So thank you very much. Thanks to the organizers for the opportunity, the invitation. It has been very nice here today to hear the other two keynotes also before mine. And I'm going to keep around the same topics, I guess. AI was a big thing. I'm also going to talk a little bit about open data that was also discussed a little bit. Just to plug a little bit my group here, just to mention that, of course, the work that I'm going to present is not my work. As you know, full professors, unfortunately, we do not do as much hands-on research as we want. We still influence and contribute to the research of our students. One of the prides in my group is that it's a very international group with all continents except Antarctica, and currently 14 people from 14 countries. The outline of the presentation, there are three broad areas. The first one, by the way, because when I talk about things I get carried away sometimes and talk too fast, please let me know, right? Because English is the native language of pretty much nobody here, so, including me, of course. So, you know, the important thing is to cover as many things as we can, but understand them, right? Rather than go through everything. So I'm going to first talk a little bit about transport data openness, and I'm going to explain why. Then a few applications, machine learning applications in transport using open data. And then in the end, philosophize, if you will, a little bit, talk a little bit more conceptually about two topics regarding AI nowadays. So transport data openness. The reason why we developed a typology of open data, public data, is because we had a project with another colleague at TUM, and the objective was not to create a typology about open data, public data, but it was how we can use them to improve model development and model calibration. And as we were talking, the PhDs, the professors, the postdocs, and so on, we couldn't understand. Very often we're saying, wait, what do you mean open? Wait, what do you mean public? And so on. And we said, if we in a room cannot understand what we're talking about, how could people understand what we're, you know, of our papers, as you mentioned before, and so on. So thinking about the way to deal with that, we found a very interesting classification that has been done many years ago, this series of concentric circles, and is not being used a lot. It is not officially published, although it exists since 2003. And this idea is that we go from broader to narrower concentric circles. And the one you see all around is the one talking about data, okay? And then the blue one is known data. And even though we are talking about the same things, right? We're working in the same fields. Now, in the presentation of Professor Lee before, I found data sources that I was not aware of, right? Even though they're available. And I review papers sometimes on very relevant topics, and I didn't know these data sets that they are using. And it's a waste, of course, right? Because we could use them to develop other things. Then below known, we have the legally attainable data. And this is also a big deal. And I'm not talking about, you know, breaking into another company and stealing their data. I had a PhD student who was working, among other things, using Twitter data, right? And he was starting, and Facebook and Foursquare and so on, and he was always starting his presentations by saying, what I'm doing here is gray area at best because it's prohibited by the Twitter API terms and conditions, but I'm doing it, everybody's doing it. Twitter doesn't really seem to worry about it because we publish openly about it, but it's something to know, right? He would feel more comfortable if what he was doing was legally attainable. And between that, we come to another set of three circles that overlap. The first one is usable. And again, this is not very obvious to everybody. There have been times that I was talking with people and, oh, we have this data, we're willing to give it to you, we negotiate, etc., and then they give me 500 pages of printed data, boom. This is not very useful, right? Technically, they gave it to me, but what do I have to do? In the end, this has happened and we have OCR'd the data, but that's not optimal, right, to scan an OCR. Another thing is affordable or gratis. Here, you could argue, but you are from TUM, Germany, you could buy the data. That's not the point. The point of free data is not that I have to ask my funder for extra money or find them somewhere else, is that I develop tools based on this and I want everybody to be able to use them. Not only people in Europe, China, Korea, and so on, but also in the Philippines, in Africa, in Greece, where funding, I was professor before and funding was not so abundant. And the other one is accessible, physically or digitally. So somewhere I can quickly download it. You will laugh, but years ago, when I was again a professor in Greece, we sent a PhD student with a hard drive to Washington, D.C. to get some data that they were willing to give us, but they could not somehow ship us the hard drive. I mean, obviously this doesn't make sense. Anyway, so here we have then this shaded thing there, which is the intersection, which is what we called public data. And then within public data, we have the holy grail, if you will, if some of these data are also redistributable, and this we call open data. Okay, so you may not agree with this. Maybe you can do another classification, but I use these 5 minutes to tell this story to highlight some of the aspects. And there are different examples. The slides, I guess, will be made available, whatever. You can have a look at them, how we can go from data that exists, but we don't have access to, right? As is the case often of smart card data or closed public transport data, etc. And then we go on to the best case, which is, for example, volunteer geographic information data, OpenStreetMaps, and so on, that are available for everybody. Now, I'm going to talk a little bit about opportunistic data applications. And what does it mean, opportunistic data applications? It means applications using data that were not collected for this reason. And I started getting involved, me and my group, with these applications with COVID. So sometimes when we know we get a new research project and we want to study something, we propose we're going to get these sensors, install them, talk to these people, get this data, make this experimental design. That's pretty, that's great. But there are cases where you cannot do it. And it's not only COVID, because you'll tell me, yeah, okay, hopefully this will never happen again, and I agree. But there are other things that come up. There are earthquakes, there are floods. You cannot instrument the entire world. We wish we could, but we cannot. So in this case, we can use existing data. And I don't need to talk a little bit more about that. These are the Apple and Google data. They have access to billions of smartphones, so they know everything about us. So they also knew things about how we behave during Corona. There is a deeper level of Google Popular Times. We've been using Google Popular Times for 5 years. We're calling it GPT. Now we don't call it GPT anymore, because if we say GPT, people think of something else. So we have to say the whole thing, Google Popular Times. And I'm sure everybody is aware of them. We have these blue bars here that tell us the historical popularity of some venues, and the pink one that tell us right now what is happening for some of these. And from this information, we can easily create these kind of trends and see, for example, that in the beginning of COVID, some visits, for example, to the supermarket or to the supermarket, the trends stayed pretty much the same. So the dashed lines are the behaviors, the average behavior on a Wednesday and a Monday, and the solid ones after Corona. Similarly, for pharmacies, we didn't have a significant drop, but for fast food restaurants, we had a significant drop, right? So this was a very simple, easy way to understand what we all knew, right, and measure it. And we developed some models based on this and so on, very nice. One issue is that these trends that I showed you before, they are relative to the maximum popularity of this specific point of interest. So we don't know what this really means. And I had a nice Russian student who was very good with hacking stuff, etc. So he said, okay, I'm going to take some Arduinos or Raspberry Pis and some sensors and very easily, cheaply create some sensors that I will take and I will go next to a point of interest, next to a restaurant, next to a cafe, and see how many Wi-Fi, Bluetooth sensors, devices do I detect, how many phones really. And then develop something like that, where you see here, this is for a Japanese restaurant near the university. Here, the blue line is the Google Popular Times trend, and the orange is the one from the sensor. So here there are two things that we can observe. First of all, a good correspondence. Okay, that's good. The second, I can now put a number to the peak that I get from Google. So from Google I get a trend, but now I can scale it, right? And learn this and use it for all times. I don't have to keep my sensor there all the time. And of course, now that I know that this thing is working well, the two things work together well, I can also get other information. So besides the number of visitors, now I have extra information about the length of stay in minutes in this venue. And this is another one, and these both work very well. Yes, not all of them work well. Some others, they are all over the place. The Google Popular Times and the devices, the Wi-Fi, Bluetooth detectors, do not correspond. They show totally different patterns. Why is the sensor working if I'm in front of a McDonald's and not if I'm in front of a Starbucks? No, it's always working, but there are other reasons. For example, if I have a restaurant on its own, then I'm more likely to capture the patterns of popularity of the restaurant. But if I have 10 next to each other, I'm a very busy place, and in front of that I have a bus stop and so on, now I'm getting some confounded effects, right? People might not go in visiting the restaurant, but they might be waiting at the stop in front. Another thing, addressing the quality of drone videography data. So Professor Lee before showed this data set, Pneuma, in his list of available data set, and it's a very widely used data set. It is a set of 10 drones together, right? As you can see here, it's how these 10 drones have been stitched together from downtown Athens, collected by Nikolas Geroliminis and Manos Barbounianakis, two good colleagues from EPFL. And this data set, we wanted to start using it for something else. So we start using it, and we look, you know, Vishal Mahajan, my very good PhD student, former PhD student, very thorough, has learned well from me. Whenever you take data, doesn't matter how many people have used them, doesn't matter who has collected them, beat them down. Try to understand them, what they mean, how they behave. So even though this data set was widely used, he plotted that and he saw maximum accelerations and maximum decelerations of 20 meters per second square, 2G. Just to give you context, if you're not comfortable with this unit, if you throw these cars out of a tall building and they crash on the ground, they will get maximum 1G. So now they're accelerating and decelerating with 2G. Okay? Something is wrong here, which is fine, and we discussed this with the people who collected the data set, and we worked together on fixing the issue. So I'm not doing a presentation. I could be doing a presentation, the whole presentation just on this, but I'm not, right? I'm trying to give you a few different applications to make some points. So if you're interested in more details, you can look at the paper. We can discuss later on the break. So what is the problem? We try to understand why these are high accelerations. Here, you see per vehicle, the different, when there was a transfer of a vehicle from one drone to the next. And we see that the big accelerations appear at the handover from one drone to the next. Whoever has dealt with video data knows what's happening, right? It's an issue with the stitching. Because you have 25 Hertz data collection, and if you miss the vehicle a little bit, you miss a frame, etc., of course you get very high accelerations. Or unrealistic issue. So once we understood what the issue is, we have to fix it. And again, you don't have to worry about this. I'm not going to go through all of this here. But we process each vehicle. First of all, use a noise filter on the speed to remove the anomalies. Then calculate the accelerations based on the new speeds. Then train on this a gradient boosting model. Create an anomaly mask based on the reconstruction. Remove anomalous accelerations. Calculate new speeds from the corrected accelerations. Calculate speeds from the anomalous accelerations. Apply a Gaussian filter on the speeds and recalculate the accelerations and so on. Again, that was all too fast. Give you an idea that we use many algorithms, and this is something that I will connect in the end. So if you think that it's arbitrary and you say, but why did you use this filter here and why did you use that filter there? This is exactly the point I will make in the end. That's what I'm not happy about, what we did and what most people do in there. But now instead of showing an example of somebody else, I'm showing on my research, which I'm very proud of, but it's the state of the art, right? We need to go somewhere else. So this is visually, quickly, what I described. So here, you see the blue line is the original accelerations. Then, when we apply the filter, we get the red curve. Then, we remove the anomalous accelerations, retrieve consistent speeds. So here, the blue curve is the original speeds. The red one is from the Gaussian filter with the anomalies. And then the black one is when we remove the anomalies as well. And then we go back and recalculate accelerations. And again, the blue ones are the originals. The red ones are the ones when we use the data with the anomalies. And the black ones, the more realistic ones, are the ones when we remove also the anomalies. Okay? And again, there is a reason, right? This all seems very arbitrary. I'll come in the end and discuss this a little bit more. This is just an idea, a way of the results, right? The blue results are the original accelerations. You see very high accelerations, and the red ones are after this processing. Another note that confirms our suspicion. You notice that the original blue accelerations, they are not a cloud, as you would expect, right? The very high ones follow some specific patterns. And this reinforces the suspicion that this comes because of the issues with the stitching and the issues of missing a frame and so on. Good. Another, I think the last example of an application. Indirect traffic flow estimation from link speeds. So what happens when we're trying to calibrate a large model or a transportation model in a large network? It is easy to collect speeds, and harder to collect link counts. And it is harder to use speed data and easier to collect link data, link count data. So what we tried to do here is come up with a way to say, okay, I'm going to collect the link speed data that are easy to collect, and then somehow transform them into count data, which I know very well how to handle. And the idea is this, right? As you see in this figure, we have a network where we have we have speed everywhere, and that's realistic, right? You know, we just need some floating car data, and we get it. But actual counts we have on a very small subset of links. So here we see with these round bullet points here, the covered links. And what we want to do is train a model that then will be able to fill in the gaps and give us estimated link counts everywhere. Not correct, but something we can use to train our model overall. And again, don't worry, I'm not going to go through every box here. There is a point why I'm showing you this, not just so that you think that my PhD students are so great. There are various steps in this process, various types of models that we use and apply and train and so on. An example. So this is a very deep model which has several types of LSTM layers and embedding layers. If we look here at the first box, the primary feature set, using only or differently, we have three levels of analysis. In the first one, we only use exogenous data, okay? Which is the most correct way to do it. In the second, the orange you see here, we also included occupancy as a predictor. So we are trying to estimate speeds, or counts, and we also include occupancy, okay? Something else that is measured. And in the top, we create an autoregressive feature set. So we also include lagged counts. So you could argue it's cheating a little bit because it's the same thing that you are predicting, but it's lagged, and you have it because you estimated it before. And then we have a number of layers, as I mentioned, right, which have, as you can see, embedding of all these categorical values, and then several LSTM layers and stacked LSTM layers with different characteristics. You see here what they mean and so on. Again, I could also be talking only about this for the entire time. That's not my point here. There are deep layers, and we use them, we train the models, we can do this. We find that LSTM is better than XGBoost, okay, based on the results. And then we also try to understand which kind of LSTM. So we play with some of the parameters of LSTM. Again, there is a reason why I'm saying all that, right? I'm trying to build up a story. So we look since we first, checked XGBoost versus LSTM. We found LSTM is better in this case with these results and with this data and so on. Then we take LSTM, and first of all, on the exogenous, with the exogenous parameters only, and we try different values of the look-back length and the prediction horizon. We find that the best combination is 6 hours look-back length and 1 hour prediction horizon. Then we tried the other types of LSTM with the exogenous variables and the occupancy, and also with the occupancy and the lagged flow. And we saw, of course, that it improves the data considerably. And then we did transfer learning. So we took this model that we trained in Paris, where there are a lot of data, and applied it to Madrid, which has fewer data. And this is where I think it gets very interesting. So the blue line, the blue line is a model that is trained on Madrid. We're using all the data that we have from Madrid. And we see here that if you have, a lot of data, you can do well. You can do well. If you have fewer data, you do very poorly. And you do not only do very poorly, but you also have a very wide confidence intervals in how poorly you do. What is the red curve here? The red curve is the model that we trained in Paris and we transferred in Madrid. How does transfer learning work? There are all these layers. We keep some of them frozen, and we unfreeze only few. So because we don't have a lot of data, right? We don't have a lot of data to train the entire network. We keep some of the structure, some of the layers frozen, fixed, and we only we only update fewer. And which ones do we freeze and which ones do we keep frozen? Trial and error, different combinations, okay? Again, state of the art, not happy about it, okay? And part of what I'm gonna talk, I want to go and talk in the end. Now, going forward, okay? So we have this thing, artificial intelligence, everybody's talking about it already today. My life is made easier now. I don't have to spend a lot of time on this black box. What is it doing? Can we trust it? Who knows? And for many years already, we have been talking about explainable AI, interpretable AI, and that's great. How can we understand what this black box is doing, right? It's very well known, as you see, Google gives 20,600,000 responses, etc. I guess everybody here understands what explainable AI is. But what is more interesting is reliable and responsible AI. And already it's impressive that it has, even though not so many people have heard about it, it has already reached the point that the EU, the European Union, has created some sort of regulation on this, the AI Act. Okay, not specifically on this, but it goes in this direction. And the OECD also recently had some discussions and some meeting on this. And now I'm going to close the loop and say, okay, but why do we need it, right? On the things that I showed you here, what could have been better? What are the limitations? And I think you get the point, right? First of all, how do we choose which layers to use, which architecture to use, in which order to set them, and so on? Trial and error mostly. Of course, we rely on the literature. Some people have found something, but they also don't know why. Maybe it had to do with their data set. Why not try it on a different data set with different properties and see if we get something different, like some different results? Because you see, even in the same data set, we get often different configurations to be superior, right? So we don't feel very confident about it. So how do we choose the architecture? Trial and error. I wrote here mostly empirically. It sounds a little bit better, but unfortunately this means trial and error. And again, the same thing here, right? Even on the same data set, the same application, and if we vary the proportion of the target data that we use for training, we see that the best configuration is different. So in this case, when we have fewer data, the best results we get are by only unfreezing the LSTM, whereas if we have more data, it is a different combination. Makes a little bit more sense. Sure, if you have more data, you can unfreeze more, but still. The last point. And this obviously here applies to most of the examples that I showed you, right? All these big flow charts, etc. The decisions we made make some sense. We have a reason to do them, but it's not clear that this is the only way to do it, or even the best one is the best one we found, etc. But there's no guarantee that this is the best one. Now, another point is the point about AI methods. And these are two papers that have been published relatively recently, 2022. And from the titles, you can understand. The first one, Metaphor-Based Meta-Heuristics, a Call for Action, the Elephant in the Room. And the second, Exposing the Grey Wolf, Moth Flame, Whale, Firefly, Bat, and Antlion algorithms, 6 misleading optimization techniques inspired by bestial metaphors. They don't mince their words, okay? And both are published in decent journals. What is the point here? The point is that in the beginning, decades ago, people came up with the ant colony optimization, bee colony optimization, but recently we get all sorts, all animals have been used in some applications. And the people in the community of metaheuristics say, you are pushing it. Okay, sure, some make sense, but now to find a different animal that does something similar and use it, and now you created a new algorithm, does not work, does not make sense. And there are different treatments here. For example, go back to the fundamentals. There are people who argue, go back to genetic algorithms, to simulated annealing, to these proven algorithms, and stop trying to invent new algorithms all the time. By the way, this discussion came up from a recent interesting discussion that we had with some reviewers about the paper that we have now under revision. And I agree with most of these things, except maybe the gray wolf. Why? I'll show you immediately. So another case, another example, which I'm only using now to demonstrate this discussion about heuristic algorithms, is an example of mixed fleet bus planning. So we have some demand, we have 3 types of buses, and we want to create a bus dispatching algorithm to decide what is the optimal way to dispatch these buses, at which one and when, right? What type of bus and when. And okay, you understand these combinatorial problems. Many of you have experience on that. Even though it looks like a small problem, the number of combinations explodes. So this is becoming very quickly an intractable problem. What we want to do is develop an objective function that minimizes the total costs meaning user and operator costs, with a number of decision variables that are the fleet size, dispatching time, and dispatching sequence. Okay? And this is a mixed integer nonlinear problem, not a problem you would like to solve, but okay, if you have to, what do? You resort to metaheuristics. Now, you see why I say it's fine if you trash talk the bat, whatever, but the gray wolf algorithm, this PhD student of mine, postdoc now, Mohammed Sadrani, found, so to speak, it's a relatively recent algorithm that has some 15,000 citations or something, the paper written 5 years ago. It's been used in many fields, not yet in transportation. This is, we think, one of the first applications. And already, before the reviewers started bashing us about using gray wolf, we had used not only genetic algorithms and the gray wolf, but also combinations of a metaheuristic of combination of genetic algorithms and simulated annealing, and also gray wolf and simulated annealing. Okay? And what do we see? We see that gray wolf outperforms genetic algorithms, and both combinations, hybrid algorithms with simulated annealing, outperform the simple versions, and gray wolf performs much, much better. And in fact, here, the one figure on the left shows the application of our model on small instances, the other one to medium instances, and these could be solved with GAMS, which is a well-known solver, exactly. We are not interested in these problems. These are small. We are interested in large scale. But in order to know how these algorithms are doing, we are comparing their performance with GAMS, with an exact solver. And here we see in the small instances that the best one practically has a 0 error. In the medium ones, also very good. It's like a 0.1% gap. 1 second. Yeah, okay. There's something I was missing, but then we see here these bars are the runtime of GAMS, of the exact solver, and the other trajectories are the runtime of the other algorithms. So you see, here it's already much shorter, but even for much larger problems, which are really of interest, it works well. And Grey Wolf is also faster than genetic algorithms. And also the combined, the hybrid, is also faster than the other hybrid genetic algorithms and simulated annealing. And this is just another indication of how well it converges. So we are done with this. Again, the last one may seem out of place, but relates, I think, to the data and AI discussion. So the first part was reliable, robust, explainable AI. This is an issue, an open issue we don't know how to deal with, but a lot of people are working on. And the second is also related to the choice of algorithms to show some, restraint, but also when there is a good reason to also consider new algorithms and hybrids and so on. And with that, I'm open to questions.
Okay, thank you for the presentation. Any questions or comments from the board? Yeah.
I'll just speak really loud. I have a very loud voice. So you mentioned responsible AI and the AI Act, which I personally love. I think they're great.
I expected that.
I know. But I've also talked to Korean government officials, engineers, a bunch of other people, and they actually see it as a hindrance to technological innovation, as kind of like these regulators or lawyers or social scientists they don't understand innovation, they're just trying to regulate us as much as possible. What are your thoughts on that as an engineer who are dealing with these problems directly?
There is a saying that, what else say? It's that they say the US innovates, China copies, the EU regulates. Okay, sorry, I don't know if negative for anybody. Yeah, they do it a lot. The point is, this reminds me of the discussion that they had when ChatGPT came out, that people were saying, okay, let's stop for 6 months. That doesn't make sense, right? Because it punishes the good actors, but those that want to abuse it anyway, they're going to keep doing it. The EU regulates a lot. It has to be global, and still it won't be effective. So yeah, I didn't put it here to say that I support it fully, more than there is a discussion in this way, which I find very intriguing. Very intriguing. I mean, GDPR, I don't know if everybody knows it, but we have in Europe very big restrictions of collecting data. In Germany, it doesn't influence so much because the country regulations were already harder already before. But the main way we notice it is that when we go to a new website, we have to click 5 times, accept cookies, don't do this, just do that, things come, etc. That's the main thing. But again, companies that want to collect our data, they don't respect it, right? They violate it and we find it afterwards. So I'm fully with you interested to see how it plays out. For you, it's closer to your research, the core of your research. For me, it's the periphery, and I'm just observing it to see what I will be able to do.
Sounds great. Thank you.
Okay. Oh yeah, go.
Hi, good afternoon, sir. I actually a PhD in the domain of the
Should be on.
I'm a PhD student in the domain of the built environment and the bike behavior. So I'm curious about the acceptance and regulation of the AI used in the prediction of people's subjective perception, especially in the large geographical area, because in the domain of urban planning, it's like so common to use AI to predict people's perceived like lively or full about the space quality. But in the domain of transportation planning, we are always be judged about the reliability of, and the credit about our data set. So I'm curious about your opinion about this matter, because it's very difficult to validate this data about the subjective perception instead of using some behavior data or some trajectory data. So it's my curiosity. So.
I'm not sure I got the point with the trajectory data. So in general, you ask, if I get your question, how acceptable it will be to use in transportation these kind of tools, black boxes, AI, that we don't have any idea about its quality. Is that your question?
Yes, because if we want to use some AI-based model to predict people's perceived safety, like this kind of thing in our large geographical area like a city, it's very hard to validate whether our result is robust.
Yeah.
So that's my question. So,
I mean, questions like that do not have an easy answer. It's the same thing as if somebody tells me, should I accept this job offer? Should I accept the position to do PhD at that university with that professor? I would say, show me the options. Tell me which other job offers you have. Tell me which other positions you have been offered, and then you choose. Same thing with this. Yeah, it's not great to have an algorithm that you don't know how it's working, but if it is outperforming other algorithms, it might be okay. Also, there is something else. Depending on the application, you might want to compare the performance of different approaches based on the expected performance, on the best case performance, worst case performance, and so on. So you mentioned safety. In terms of safety, for example, you might not be okay, or in safety-related, safety-critical applications, it might not be enough to have the average best performance, but you might want to make sure that you don't have a very high risk for some people. I don't know if this helps as an answer, but.
thank you, sir.
Okay, it's just back.
Thank you for the presentation. I have a question regarding the data set. So I'm mostly interested in travel behavior modeling. So my goal is actually infer the travel activity purpose in individuals. So data that you introduced us as a Google popular time graph, which is I didn't realize it existed. So do you think I believe it provides the popular graph for each locations? Is it correct?
No, not for its location. In cities, there are thousands of points of interest that it covers. So we have used it, besides Munich, we just finished another project where we used also with partners Kyoto, Madrid, I think Budapest, and so on. And there are maybe more than 10,000 points of interest only with historical information, and a couple thousand with live information, I think, in Kyoto, for example. So this is the order of magnitude of data.
Okay. So do you think it can be somehow used as a validation tool to creating data can be compared to this popular graph, or it can be used as a weight somehow to generate data?
It can be used for many applications. As I mentioned, in this project that we discussed, we try to use it to create demand. The problem is that you want to create activities, right? And for what you mentioned, travel behavior. The problem is that this does not give you this information. It doesn't link. It links activities, but you cannot easily create ODs, you cannot create trip chains, and so on easily. You have to approximate them, you have to be creative. But it's some very rich data set, not rich, but very interesting data set, potentially useful, with many applications.
Thank you.
But you have to be smart about how to use it, right? Innovative. But there's a lot of research on that. We are not the first ones to come up with it or to use it or to invent it or anything like that.
Thank you.
Okay, well, any other? Yep.
Hello, Professor. Thanks for presentation. About the open data, I think in some areas that the open data sites, these resources is quite abundant. For example, in the United States and Manhattan, the open data is quite abundant, and you can train many models and to find some interesting findings. But in some areas, for example, if I want to do some research in my area, and I have said, and I think in your slide you had mentioned that you try to transfer the models to other areas. So I want to know what is the most challenges in this process if you want to transfer a model in one area to another area.
Yeah. So that was also the motivation for us to do the research with the transfer learning. And something that I forgot to say before, and you could have asked me to say, okay, yeah, sure, but you transferred the model trained in Paris in Madrid. You expect that it will work well, but if you transfer it to New Delhi or to Seoul or to Beijing or I don't know where, to Lagos, it will not work as well. Yes, obviously, we are at the first stages now, so we say, I look at a similar city which has the structure and I use this structure. And this applies to, first of all, your first point, where there are data. That's why I mentioned opportunistic. Did you see any example here from Germany, except for the one that we did with Google Popular Times and with our little sensors? No, because of the data limitations in Germany, data protection limitations in Germany, there are not so many data open. We use whatever we can. We use the PEMS data from California, we use the open data from Paris, from Madrid, from anywhere we get them. So as researchers, we're relatively free because when I publish a paper, nobody really cares if it is based on using data from Paris or Munich. But if I want to do a project in Munich or make it more relevant, then I have an issue. For us, that's an issue, right? We go where the data are until there are more data available. Some of these sources are available for pretty much everything, right? So Google Popular Times, I was in Phnom Penh recently and so on, and you could get a lot of information because you don't depend on anything else, right? Everybody has a smartphone nowadays, or a vast majority of the people, so this kind of data can be collected.
Okay, thanks.
Good.
Okay, well, one last question from Lee.
Thank you. Thank you for your presentation. I'm Sujini from Professor right? So I have two questions. The first one is about popularity trend. So I think depending on data set you choose, the trend might be different because even for the same travel demand data set, the taxi travel demand and bus travel demand is totally different. So is there any know-how to select the data for explaining this kind of popularity trend?
So again, here, the Google Popular Times just tell you how many people are sitting in this restaurant. Doesn't tell you how they came there. So this is different things. That's a related question from somewhere else. How can I use this information to infer something else? And there we have to be creative. We don't have so much information. We have a couple of projects where we try to get more information from these Wi-Fi detection, Bluetooth detection sensors by re-identifying, for example, people and so on, and creating chains. But that was also broken because a couple of years ago, the smartphone manufacturers, for privacy reasons, started randomizing the MAC IDs. So you cannot even do that. But this is a limitation. We don't have this kind of information. We cannot re-identify people.
Thank you. And I have a question about the contribution of AI. So after introducing AI, we can predict the link speed and travel time. So we can we can select some optimal route for our journey. But I think the road condition is not that improved that much. So, so do you have any idea to solve this kind of gaps between AI introduction and the actual road condition?
So first of all, the fact that using AI will give better results, etc. Your words, I don't say that, right? We hope. Actually, my view, just because you raised it, is that we've had only conventional methods. Then AI came, and everybody, including me, started using only AI, low-hanging fruit, etc. But already years ago, we have started to try to go into a second generation of big data analytics, where we combine all the information that we have, all the traffic flow theory, and all the models that have been developing for the last few decades with machine learning to get something stronger, something more capable. So this is a footnote to the first part of your question. To the second part of your question, you say road condition. I guess you mean traffic conditions, right? This is a big question, because there are also the issues of induced demand. So people believe, and including me, that if you, for some reason, you manage to improve considerably traffic conditions, let's say a typical example that has happened many times in the US is there was one bridge in Boston, for example. It was 3 lanes and 3 lanes. They built a second floor, and they doubled the capacity. After 6 months, and of course the day it opened, everybody was going well. In 6 months, they had the same travel time as before, and double the number of vehicles, double the emissions. Why? Induced demand, right? So by somehow magically improving the flow of vehicles and creating residual capacity, this residual capacity will be covered. Because now, instead of going to shopping in a store that is 10 minutes away, we'll say, oh, there's a better one that used to be 45 minutes and I wouldn't go, now it's 25 minutes and I'll go. And we create this issue. So we humans are very unusual and strange animals, and create these kind of paradoxes, which are very, very interesting. Sometimes people say, and I close, that we shouldn't improve traffic conditions or the roads to the downtown, not improve the signal coordination, but actually make it worse. Stop people at every step of the way, make sure they stop at every traffic signal. Why? Because we discourage people from going to the downtown. If we push as many people will come into the downtown, then everything will gridlock. So it's a little bit more complicated than that, how we use the methods, but we develop them, and then we have to help the policy makers decide how to best use them.
Then can I have one more?
I think we can leave it for the discussion session.
Okay.
Well, yeah, just say that for discussion session. Okay, now it's actually I think it's very now. And thank you for the presentation. It was this. So please give me one.